Welcome to Beyond the Microchip, brought to you by Microchip Technology. In part one of our two-part episode on alternative PNT and Hollywood spy thrillers come to life, we discussed how popular depictions of positioning, navigation, and timing technologies in movies and television reflect a deeper reality than we may have previously thought. In part two, we continue our conversation of these ideas and dive into the products and systems that support alternative PNT. Thanks for listening. Can you talk about the national timing grid? You started to get into countries and time, but this is a very interesting idea of a country wants to have its own time.
Yeah.
Can you get into that?
Yeah. Countries are realizing that time is a utility that's similar to electricity. So the idea of a national timing grid is very similar to the idea of a national power grid, right? And so, being able to have control of the source of the time, right? And have that source of time be located on the soil of their country, or maybe have a source of time that has another backup source of time, and yet maybe even another third location as a source of time, all on their country. Then from there, distribute time from those sources to other key locations, right? Those distribution techniques, again, could be, as I mentioned before, it really is dependent on what's available and possible given the terrain of that country.
Mm-hmm.
All options are available today, whether it be fiber, RF, or even alternative satellites, not GNSS satellites, but alternative satellites.
Right. So you talked about terrestrial satellites?
To me, it's kind of a satellite, the forgotten satellite, the geostationary satellites.
Geostationary, that's what I was thinking of.
Geostationary satellites. They're interesting because they've been around a long time. And just to kind of put it as a point in context here, where a GNSS satellite's 12,000 miles away, a geostationary satellite is actually roughly, let's say, 22,000 miles away. But it's geo, it's in a fixed location.
Right.
Okay. It's moving a little bit. All satellites do, but it's not orbiting, right?
Its job is to find a spot.
Yeah.
That it's right above.
And stays there. Geostationary satellites have been around for a long time, are still very popular today and used for everything like broadcasting of live sports events, for example. What's great about them is they're a very convenient way to perform time transfer, right? So if I wanted to have 3, 4, 5 key locations, I wanted to interconnect them separate from GPS or GNSS, I could use a geostationary satellite to do that.
Right.
And
they're high enough that they can see each other, right?
Well, I probably, depending, you just use one geostationary satellite,
okay,
right? You just really need one, and the 5, clocks on the ground could actually trade time with one another, like I was talking about time zones before, right?
Right.
And know how far off they are from each other. And so this kind of creates a backbone for the grid, if you will, right? So you got your source of time. You can start thinking about ways to build a backbone for that timing grid. And then once you've got that backbone constructed, you can find ways to disperse the time out more towards the edge of the network, okay? And many times countries will utilize something like fiber optic, right? They're shorter runs. They're able to lay the fiber in those different parts of the country cost effectively,
mm-hmm.
and distribute time that way.
So before, when you talked about the 4 different constellations, they've got names. So GLONASS was Russia, Beidou was China, Galileo was Europe, and ours is GPS.
Right.
So GPS it's what it is, it's what it does. But all 4 of those are interconnected. They can work with each other?
Well, they're not interconnected.
Okay.
At the space segment level, if you will,
right,
or at the control segment level. But at the user segment level, most receivers today can, in fact, receive PNT from all 4 of those constellations.
At the user level.
At the user level,
got it.
exactly.
Okay.
Which is another, hard to believe that a little receiver can receive all those satellite signals, but they can.
Yeah.
What's nice about a a GNSS receiver, it's configurable, it's programmable device, right? So you can select what constellation you want to receive. And in many cases, as countries are looking at national security concerns, they're being more selective about what satellites they're going to make use of. For example, if they want to make use of Galileo, or if they want to make use of Galileo and GPS only, they can configure those receivers to do that.
Right. And there's potential for geopolitical concerns with that.
Absolutely.
Okay. When we talked about there's LEO, there's MEO, and there's GEO, and low Earth orbit, I think, as you said, is somewhere around 1,000 or 1,200 miles.
LEO actually gets down to like 300 to 400.
Right.
Okay. It's in.
But those are the
those are
close is a relative term, but 300 miles is the closest that it gets. That's low Earth orbit. But those are moving, right?
Oh man, they are moving. They're moving fast.
And then mid Earth orbit is where you said GPS is, and then once you get up to GEO, that's geospatial. They don't move at all.
Correct.
Okay.
Yeah. One thing to keep in mind on PNT is it's kind of like UTC. It stands for position, navigation, and timing. But really, when you break it down, I might get a little geeky here, right? A little technical, but timing is the most important of the three.
Right. The big T.
You could argue it should be called TPN, right? Because you kind of need the timing first,
right?
Figure out the position to figure out the navigation. But I guess, TPN is not as cool sounding as PNT.
So when we get into alternative PNT, complementary PNT, multiple PNT, what kind of technologies are we talking about? This is where we can kind of get into some technical aspects of it. We have the command, we have the space, and we have the user. And obviously they're going to talk to each other somehow. Is that where Microchip comes in?
Yeah. I mean, let me say that I'm going to reference back to this workshop I just was at last week.
Right.
Because this was a big topic. And, point one, right, there's not going to be one solution. And it was fascinating to me to see the range of solutions that were being proposed. I mean, I saw presentations on using traditional broadcast television signals as an alternative PNT system.
Yeah.
Right. All the way to the latest and greatest in low Earth orbit. Okay. As an alternative PNT system. Right. And we've talked about some of these alternatives like terrestrial, like, fiber optic or RF. And there's even technologies, I don't know how to say it. It's like Back to the Future in a way, right? There's a technology that was what our PNT infrastructure depended on pre-GPS, which was called LORAN-C. But LORAN-C was the over-the-air RF-based PNT system that certainly the United States and some other countries across the globe used.
Yeah, I got it here. LORAN-C is a hyperbolic radio navigation system that allows a receiver to determine its position by listening to low-frequency radio signals that are transmitted by fixed land-based radio beacons.
Yeah. And LORAN-C, again, worked wonderfully, and it was a land-based system.
Mm-hmm.
But, GPS came around. I remember when it came around, it was people looked at GPS like, a satellite's kind of far away. Does it really work? It's interesting how it takes time for technology to adopt.
And it comes back around. Yeah. I mean, they're all effectively radio signals, right?
Right. But the point here is that got a Back to the Future effect happening here. The LORAN-C is reemerging as a very important alternative PNT. It's now called eLORAN. Okay, enhanced LORAN, right? Mm-hmm. We've been involved with a lot of field trials of this technology. There's, other countries across the globe, particularly in the UK, most notably, who are very much looking at eLORAN as a key technology because it's ground-based, it's RF-based, so it really removes the space segment, and it puts the source of time in control, in the control of the user. As I mentioned earlier, it's an excellent alternative. So I think we're going to see all of these. I think the point here is the answer to the problem is multi-PNT. Mm-hmm. That's the answer. And what we're doing at Microchip is designing systems that can take in any of these references: eLORAN, broadcast television signal, low Earth orbit, fiber-based time transfer, two-way satellite time transfer over geostationary. The key is to have a platform that can take in multi-PNT, which kind of brings me to another really important point. And, I love analogies, we all do, but, let's look back at a data center, for example, right? Data centers, they do consume a lot of energy, a lot of power, right? I mean, they're looking at ways to lower that. And
some of them take up the amount of power that a country would consume based on one of our earlier episodes.
And, I'm not an expert in this particular area, but I believe that most of those data centers have backup power, right? I mean, because their source of power could be lost,
right?
And what are they going to do, right? They got to bridge through that, right? They got to be resilient in the case of loss of power,
right?
Okay, so same holds true for this whole thing of PNT, and as well as alternative PNT. Everything we've mentioned so far are great alternatives, but you still need a backup. Okay, you still need that battery backup, if you will, right? And in the case of timing, the battery backup is what's called a clock, okay? And in the case of the type of systems that we provide, that these critical infrastructure operators are using, they're using an atomic clock, okay? I mean, an atomic clock is incredibly stable, and it's able to hold that time for very long periods of outages and kind of be able to continue to enable operations of that data center or of that airport operations or, of that railway system or whatever that mobile network, whatever the critical infrastructure is. The backup battery for time is an atomic clock.
Right.
Okay. And
most people associate, and many of our other episodes in this show are focused on silicon.
Yeah.
What is at the component level? What is at the silicon level? And I don't know how many people might understand that Microchip makes systems as well. You're talking about a complete system.
Yeah. The atomic clocks, what I'm talking about are atomic clock systems that, first of all, they can range in size. Okay. We have atomic clock systems. For example, we have a product that's described as an active hydrogen maser. This is about the size of a small refrigerator. This is the most accurate clock in the world. Okay. Then we have clocks that I'll say are about the size of a loaf of bread. Okay. They're cesium clocks. These clocks are the most stable clocks in the world. Okay. Then what we've been able to do at Microchip is miniaturize this atomic technology, let's call it. We have, for example, a product we call the chip scale atomic clock.
CSAC.
CSAC.
Right. Yep.
Yeah, exactly.
Yeah, we're going to have an episode on that, I think.
Okay, awesome. Because it's amazing how we've been able to take atomic clock technology and shrink it down into this small form factor, and provide it with extremely low power consumption. Unbelievable. We also have another product we call the miniature atomic clock, which is a rubidium-based atomic clock. Again, very small, mounts onto a printed circuit board. So it's kind of like batteries. I'm going to go back to that for a second, right? It's like, how much backup do you need? How accurate does the clock signal need to be if you were to lose your reference? How long do you need to be able to maintain? How stable do you need to have that clock signal after you lose your reference? Okay. Does that battery need to exist in a really small form factor, potentially to be deployed on a tank, okay, or something like that? Or is it going to sit in a rack in a data center, right? There's all these different factors to consider on how much backup you need, if you will, right? We'll use the word holdover.
Right.
One of these alternative, you can have 5-6 alternative PNT sources, but at the end of the day, you still want the backup.
Well, you can't lose time, right?
You can't. It's just like power. I mean, I'm sure a lot of these data centers have multiple ways that they get power. Power grid has multiple ways that it gets power, right? It's getting more and more wind. It's getting more and more solar, for example. But still, that battery, that holdover, that backup is ultimate. And in time, the battery is the clock. And it's typically an atomic clock.
Suppose one of our listeners has a use case for this technology. Where would they go? Where could we send them?
Well, we have great information on microchip.com.
Mm-hmm.
If you just go from the homepage and click on the clock and timing section under the products tab, there's just an abundance of information, white papers, more and more videos.
Mm-hmm.
Because this topic does have its complexities to it, but we break it down. Videos are a very effective way to do that. That's one location. For those who kind of want to get the 101 course on GPS, a site that I like to go to is www.gps.gov. Okay, it's a site. It's a government hosted site, and it's focused on civilian GPS, right? So it doesn't get into all the military stuff.
Yeah, global public service brought to you by the U.S. government, gps.gov.
Exactly. And I think there are some great little tutorials there that really break down what we already talked about somewhat, right? The control segment, space segment, user segment, and gives us some nice tutorials of what's going on, and also posts the latest news. And not only on GPS, but on alternative PNT. Okay. Because, another interesting thing, since I've been in this industry a while, and this industry has a community. It's fun to go to that, like that workshop last week.
Mm-hmm.
I'm seeing friends, right? I'm visiting with friends. Sure, there's competitors there as well, right? But, we're friendly competitors.
Yep.
Put it that way. And what's so cool about this community is that they are really working together. And, the number one advocates really for figuring out alternative PNT solutions have been the very people that created GPS in the first place, right? They're the ones that see the problem, that understand the potential magnitude of the problem, and are the ones that are really pressing to make and get our country to do something about this.
Well, you mentioned that earlier.
So
there's creative people looking to harm it, and there's also creative people looking to protect it.
Absolutely. And there's a lot of really smart, good people doing amazing things with passion. It's always something I like to see.
I found this link while we were talking here, microchip.com/clock. Will take you to clock and timing and some of the things we've been talking about today, GNSS, atomic clocks, and all of our clock solutions. Yeah. At this point in the show, Greg, we usually get to predictions. Do you have any predictions for the future of this? Where are we going?
Wow, that's a great question. Well, there's one thing's for certain. Our lives, our world is going to get more and more dependent on PNT. That's a fact. I don't think that's a prediction, frankly. I think that's a fact. That dependency, it's not just about, playing Pokemon, or having your navigation for your Lyft or Uber ride. I mean, I'm talking about dependency that, safety of life kind of dependency, right? And that's happening right in front of our eyes. We're seeing it, across the globe. It's frightening at points, but, there's good use of PNT that's protecting it. So it's going to become more important, critically important. Figuring out and solving this alternative PNT answer, I'll say, is going to happen as well. But I'll say it again. It's going to be a multi-PNT solution. There's not a silver bullet here. Okay. Remember, we allowed ourselves, I think, to get into this leader follower model, right? At a massive scale, which has caused us to have a frightening single point of failure. So we're going to move to a multi-PNT solution, which is going to have these attributes that I described, right? The attributes of being more decentralized, being more distributed, having the great battery backup or the atomic clock, right? By having all of these alternatives and sources built into simple to deploy systems is going to give us the outcome that we're looking for, that magical word, resilience, right? That's what we're really after here is better PNT resilience. So, we're going to work together to get it done. There's a community out there that I'm proud to be a part of. I have absolute confidence that we're going to get this done and we're going to be in a better place. And, we're not going to be worrying about scenarios that we were talking about at the beginning of this podcast, right? I mean, the scenarios that they're movies, but they're not anymore, right?
No.
And
with resilience, we can leave jamming and spoofing for the movies.
Exactly. Where it belongs.
Well, entertaining, illuminating, and of course, like all great movies, we want more. Thank you for joining us, Greg.
Thank you for having me, Dana.
Greg Wolf is Senior Technical Product Marketing Engineer at Microchip Technology, working out of the Frequency and Timing Systems Business Unit. He joins us today from our global headquarters in Chandler, Arizona. Thank you for venturing beyond the microchip with us. Join us next time as we continue to explore empowering innovation to enhance the human experience.